All right, that was a great keynote. I was blown away by it. And welcome to the architecture track on the first day of Spring 1. And we're going to take what was said during the architecture track, and it's going to go directly into our first session in this track, Resilient and Adaptable Systems with Cloud-Native APIs, with Olga and Spencer. So Olga, Spencer, take it away.
Thank you, Craig. Welcome to our talk, Resilient and Adaptable Systems with Cloud-Native APIs. My name is Spencer Gibb. I've been on the Spring team as the lead of the Spring Cloud core projects for the past 7 years.
My name is Olga Maciaszek-Sharma, and I also work on the Spring Cloud team. I mostly work these days on Spring Cloud Load Balancer, Spring Cloud OpenFane, and these days also on RSocket Routing Broker. So today we'll first think a bit about what cloud-native APIs are. Then we'll discuss the protocols that are often used. We will speak about gateways. We will discuss architectures, and then we'll do a short demo of some new features. And then there will be a separate Q&A session.
So first, we want to discuss the question, really, what is a cloud-native API? Next slide. I really appreciated Ajay's talk today. It meshed really well with a lot of the things we're going to talk about. One of the things he mentioned and that we thought of when we were first discussing this talk is that cloud-native APIs are API first. Really, the API is the product. Next slide. Today, customers can interact with your APIs through various ways, whether that's mobile apps, web apps, or IoT devices. In some cases, companies like Stripe, which is a payments API company, or Twilio, which is an API for text messaging, that literally is the product, but not on all cases. Even products without public APIs have private or internal ones. You might interact, you might not interact with a public API from a streaming service or from some big box retailer or from a shipping company or from even our company, VMware, but rest assured, they and us, we're all thinking and writing APIs first. So cloud-native APIs are really composed by cloud-native systems. And not just cloud-native apps. We've heard about those for a long time. And there's individual instances, there are networks, there are load balancers, but all those things together acting cohesively are the API. And all the characteristics of cloud-native applications bubble up to the API, such as resilience and fault tolerance and rate limiting. And rather than applying just to the individual services, these attributes are now part of the API. And that makes the API greater than the sum of its parts.
Another trend that we see a lot these days is serverless. I like this definition by Mike Roberts, which is that serverless is server-side architecture running stateless, event-triggered, ephemeral compute containers. So there are two trends that we see when it comes to it. First one is backend as a service. Here, usually there is a lot of logic run on the client side, and then there is data taken from various backend services, often on a subscription basis. And the other trend is function as a service, where we encapsulate our logic in single functions that are then run in containers which are usually spawned as we get an event requesting some data that this function calculates, and very often they're stopped after. So it is basically event-driven, and it has a lot of plus points, mostly the fact that the infrastructure management is handled by cloud providers. So we don't need to worry about things like capacity, provisioning, and patching. Also, with this model, we get automatic scaling, built-in high availability, which is in the center of its approach, and also pay-for-use billing model. So we only pay for whatever time we use of this container running or memory. And this, of course, gives us enormous flexibility. This also brings along emphasis on short startup and low memory footprint. So when we optimize our applications, there are various things that we can try to optimize. For example, we can optimize peak throughput, or we can optimize rather for short startup and low memory. So if we're going for the second scenario, and this is what we will usually do with serverless use cases, a lot of times we want to use technologies such as GraalVM native Java images, which will allow us to spawn our applications really fast, and also they will use very little memory, and thanks to that we will simply save money. So in order to meet these needs, the Spring team has introduced Spring Native initiative, which provides support for native GraalVM based images for Spring applications. However, serverless also, of course, will have some drawbacks as any approach. So when we think about this, we have higher system complexity. Then, of course, monitoring and tracing also becomes way more complex. And we are also at the risk of vendor locks if we adjust too much to a certain vendor tools. And then there's something, so actually just last week, I was listening to Neil Ford at DevOps Poland, and he mentioned that he thinks serverless might also be posing risk of what is called the last 10% trap, where 80% of things that you might want to do are very easy to get done, 10% are difficult, but there's also 10% where things are just impossible to implement. So we don't know if it will really go this way, but he was saying that this is something might looking for. When it comes to support for serverless and serverless functions, we have a project in Spring Cloud called Spring Cloud Function that allows you to register your functions as beans in this very simple way that you see in the slide. And it allows you to implement your business logic via functions, and it also provides support for Spring Boot features on serverless providers. And what I think is super important, it provides a uniform programming model across different serverless providers. So another layer of abstraction to help you avoid this kind of vendor locks. Also, Ajay has just announced Tanzu application platform. The platform allows for easier building, deploying, and operating applications in Kubernetes-based systems, enhanced developer tooling, supply chain automation, and separation of concerns between developers and operators.
Next, we'll talk a little bit about efficiency and speed. So responsiveness is important, not just responsive like a responsive web app, but responding to changes in the environment and in the network, and the ability to optimize for availability and speed. It's also about protocols. The web was initially built on text-based protocols, but we will modern APIs can use binary protocols to gain some of this efficiency and speed. And infrastructure is important, right? We'll hear about that during the rest of our the rest of Spring 1, but scaling and resiliency definitely have an impact on our APIs. And like Ajay mentioned and Olga just did, whether your infrastructure is straight Kubernetes or You'll hear more about Tanzo Application Platform in future sessions. And then the Spring ecosystem, which allows us to focus on your core business. Speed to market matters too. It's like Josh says, when you use Spring, you're pair programming with the whole Spring team.
So also the cloud native APIs are now very often evolving. So this is something that we now see as a usual approach in microservice-based ecosystems. And this makes a lot of sense because as intra-service communication has become part of the functionalities implementation, it is at the center of our system. So obviously, if we want to change or broaden or just develop further our implementation and add more features, and this is at the core of it, we need to be able to evolve it. Also, it has become possible because now a lot of these APIs are just not on the edge to communicate with external systems, but are within our systems, so our teams actually control them. However, if we're going to do this, so evolve APIs, we need to put a lot of attention on backwards compatibility. That is because in a microservice-based ecosystem, we need to be able to decouple our deployments. We need to be able to deploy any of the services independently. So we cannot allow for a fact where in order to achieve compatibility with a newer API version, we will also need to upgrade and deploy a bunch of services that communicate via this API. We cannot do this. So there are various approaches to it. One is addition only. So we will never remove anything from the API, only add. Another is tolerant consumers. So that the parts that read the APIs, read these responses, will only use the data that really matters to them. So it's a scenario-based approach, not a schema one. They don't care if something changed in the response fields that they do not use for their business functionalities. And then we have deferred updates, which is an approach also present in database engineering. And basically, what we want to do is just first add something new, then wait until all our clients or all the services that communicate with us have adjusted to this change, and then only remove that. So in order to make this safe, we need to be able to ensure that the integration does not break, and it has become a key concern for us. This is something that has led to the increased popularity of consumer-driven contracts, where the parties, so the clients and the producers of the API, define a contract that specifies what the API looks like. And there has to be a mechanism in place that ensures that the producer, the business functionality and what the producer does, the API on the producer side, actually is in keeping with that contract. This is an approach which is collaborative, so both parts work together on that. Scenario-based, again, not schema-based. It provides for fast integration testing, and it allows us to test that backwards compatibility of our APIs, because then when we have a deployment pipeline, we can verify our new code against the new contract, but also against the previous contract, and then we are sure that we are actually backwards compatible. The Spring team provides the Spring Cloud contract project, and you can see an example of our contract. As you can see, it's quite intuitive. It has requests, responses, methods, etc. It provides WireMock.json stubs for HTTP consumer integration tests, messaging route setup for stubbed messaging tests, and automatically verifies the actual producer API against the contracts. So it provides fast but also reliable tests. There were various presentations on this project in previous Spring 1 editions, and the recordings are available. So if you are interested, go and see that.
So our APIs are in distributed systems are built upon some kind of wire protocol. So we're going to talk about some of those and how they fit into this cloud native API ecosystem.
So the first one that comes to mind, the one that everyone has seen, used, etc., is of course HTTP. So as we know, it is actually a document-based, resource-oriented protocols, and it was created with simple CRUD operations in thought. So creating resources, updating them, deleting them. But it is also very easy, simple, and straightforward, which is probably why step by step it has started to be used in scenarios which are way more complex than just simple CRUD operations. And even in use cases that really go very much far beyond that resource-oriented approach. This, of course, has started to pose a series of issues because of the protocol not being exactly created with the thought of what was later being used for. So first of all, we have head of line blocking. So only one request, one standing on a connection at a time can be there with HTTP 1 anyway. Then we have this client server or request response approach. So a lot of times we'll have situations when our clients will keep polling the servers to check if anything has changed because there is no easy push mechanism where the server can just inform us of some change. It is also synchronous, and because it is typically TCP based, there is a lot of handshake overhead for every connection. And as there is the head of the line blocking problem, we usually have various connections open, which is not very efficient. Also, HTTP1 is text-based. So I really like this quote by Rüdiger Müller that the internet is running in debug mode. So we get these nice text JSONs, and it's very easy for us to read them and debug them. But they're not necessarily the best way for machines to communicate, definitely not the most efficient ones. So HTTP2 is trying to address a lot of these issues. So it is a binary protocol. It is also a multiplex protocol, so it allows for parallel requests to be handled over the same connections, and it removes the order and the blocking constraints from HTTP1 protocol. It also offers some header compression and a server push mechanism that is, well, better than nothing, but it's not exactly still what we are looking for. It is a client caching solution. And now the upcoming plans are for HTTP3 are quite exciting because there is a plan to make it QUIC-based, and QUIC is a multiplex transport that is built on top of UDP, so much less overhead at the beginning of every connection.
Message-based protocols are increasingly important in the cloud-native landscape. These allow other interaction modes beyond just the request response that Olga just spoke of. Message brokers like RabbitMQ and Kafka offer this distributed messaging and streaming semantics that are super interesting. They allow different interaction models such as topics and queues. Topics are one-to-many, so one message can be seen by many consumers, and queues, which are one message gets seen by one consumer. So depending on the needs of your application, you can pick between these different kinds of interaction models. Messages can be durable or ephemeral. Durable means that the message is persisted to some kind of storage device, and this allows, for example, for high availability and resiliency. Consumers can come back and read those messages even if there are some kind of network failure. And messaging allows for separation of concern at the API level. That means that consumers who are interested in a particular set of data can just listen for the appropriate messages. There doesn't have to be tight coupling between services in our microservice architectures. And architectures such as event sourcing and command query responsibility segregation, or as most of you probably know it, CQRS, depend heavily on these message systems. I know there are some talks later in the conference about event sourcing, so watch for those.
Another protocol which is quite fresh and new, but we think it's really interesting, is RSocket. So what RSocket does is take the reactive stream semantics that, again, I guess many of you know, onto the protocol level. So with reactive streams, we see the responses that we are getting as streams of events or streams of data that we can later filter, map, we can handle errors, and so on. And one of the very important things here is also that we have the so-called backpression. So the subscriber can request an n number of events or of elements of the streams, and therefore there is no congestion. So the RSocket protocol models all communication as multiplex stream messages over a single network connection. And that's why it never synchronously blocks while waiting for a response. So it's message-driven and fully asynchronous. Also, it has various modes of operating. So we do not have anymore only request response, because let's face it, our scenarios often also require very different interaction models. So we have also fire and forget, where we just send something and we do not care about what we get in response. We just don't get the response at all. Then we have, of course, the traditional request response, but we also have a request with a stream response. So we expect to get a stream of elements or events in our response and not just one. And then we have the bidirectional channel. So both parties can just communicate in whichever order they like over that. It also has inbuilt flow control. So first of all, we have this back pressure mechanism, which works exactly like with reactive streams. You can just request a number of elements. And it also has leasing, which is a way for the servers to signal their capacity. And this is very handy with load balancing, for example. It is binary, and it can work over a variety of transports. So we have TCP, but we also have WebSockets, ARON, which is a UDP-based transport, and in the future, there is planned support for HTTP free and quick.
So next, we'll talk about gateways and how they are part of this cloud-native landscape, these cloud-native APIs, and how important they are, especially with regards to protocols and stitching our APIs together. First, there's an important aspect that we need to talk about before we get directly to gateways.
This aspect is discoverability. So before, some time ago, we could just assume that we could hard code our hosts and ports and just be happy about knowing where the applications are. And even then, many years ago, it was considered as one of the fallacies of the distributed computing to think that the network topology doesn't change. But now this process has sped up a lot. So now it's changing constantly. We have the serverless containers coming up and just going down. We have Kubernetes containers also just being created all the time and then destroyed. So we cannot rely on the client knowing where the server instances are. So a popular approach to solve this problem has been service registration and discovery, where we use a service registry where all the services register their instances. And the service registry also has knowledge about the health state of the instances. So then when a service wants to connect to another one, let's say service A, it will first query the service registry for the instances of service A, and then once it knows the right instances, and maybe there is some kind of load balancing mechanism also involved to choose the best one, it connects and it gets its response.
So the first gateway we'll talk about is Spring Cloud Gateway. Ajay mentioned Spring Cloud Gateway in the keynote this morning. I was super excited to hear about that. Spring Cloud Gateway is developer-friendly API gateway. When we built it, we focused on the developer experience. So Spring Cloud Gateway is just a Spring Boot application. We want to say deployments, not tickets, right? This is not your old ESB. So Spring Cloud Gateway really is the glue for your HTTP-based APIs. You connect different microservices to act as a cohesive API, and it doesn't really matter what your clients are on the other side because they only interact with Gateway, whether they're a mobile app or web app. Look for sessions in the conference about Spring Cloud Gateway. Also, look for talks about API discoverability that are based on Spring Cloud Gateway. Those are very, very interesting. Gateway is a place where you can apply cross-cutting concerns to all the services that make up your API. Ajay talked heavily about security and how important it is to secure your applications. Gateway allows a single place to make that happen. Complex things like rate limiting can happen in the Spring Cloud Gateway. Fault tolerance, so things like retries and circuit breakers can happen at one place in Spring Cloud Gateway. And obviously something simple like load balancing, where you pick between instances of a particular service. Also, something else that I've talked about before and that Jürgen mentioned was RSocket. So we're going to talk a little bit about RSocket Broker, which is a specialized message broker for the RSocket protocol that Olga just spoke about. So again, this is an interesting place. I'll talk about where you can apply security, that same kinds of fault tolerance. Fault tolerance is a little different because of the RSocket protocol itself has things built in. Load balancing can happen in this centralized broker, and I'll talk a little bit about how service discovery works when we show a diagram. So RSocket Broker works by having a small cluster of broker instances. In this particular diagram, I have 3. As services come up, they register directly to the broker when they connect. So each broker node communicates with the cluster, and you get a full picture of all the services that are connected. And so the broker becomes the de facto service discovery mechanism. And interestingly, for security, these services can block all incoming connections because all incoming requests come over the connection the outbound connection they made to the RSocket broker. So they're extremely secure since no one can make any requests to those new connections to those services. Load balancing is done as a service makes a request. They pass a little bit of metadata called tags to the broker, and then the broker can select the appropriate instance or subset of instances that the request should go to. So the broker allows for additional interaction models, such as broadcast messages as opposed to just single instance messaging. Also interesting here is that Spring Cloud Function has RSocket integration. And with that, if you need durable messages, you could send those messages through RSocket to something like Kafka or RabbitMQ that we spoke about earlier.
So we really spent some time talking each year about this protocol and about the broker, and we're trying to make it popular because we think it's a great piece of technology. However, we also do realize that a lot of people just have these systems that are already built on top of different protocols, and that is not easy sometimes to just change the system overnight. It is just impossible. So of course, then what we usually want to do is create some kind of adapter where our systems can still communicate, even though some parts are using different protocol, but then some parts are using a newer one. And we decided that we were going to make it easier for everyone. And we have developed the RSocket HTTP bridge that does just that. So the bridge is actually just a small dependency. It's a module in RSocket routing broker, and it is built on top of Spring Cloud Function. And it allows you to do HTTP posts to that broker, where you will just specify your service ID and then your RSocket endpoint. And it is very similar to the way that the Spring Cloud's HTTP stack support worked for service discovery, load balancing, and so on. So you just pass this information, and then you pass your payload, for example, as a JSON, because that's how your system is talking right now, yes? And then you can also pass information, so you can pass tags as headers. And what the bridge will do, it will just parse all this information, connect to the broker, and connect it to a payload operating with byte arrays, and then through the broker, pass it to the right RSocket service instance and endpoint. So the method that we support is post. We support byte arrays as our content type. We also allow passing tags as headers, as I said. And you can also specify the interaction mode in the URI, so the fire forget or request response and so on. If you do not specify it, our default will be used, which is request response, but you can also specify your own default for all the communication. We also handle well-known key, so this might be an interesting bit of information for those of you that already use the RSocket routing client and broker. The well-known keys are a predefined way of specifying certain information that allow you to choose the right instance, such as, for example, instance ID.
So now that we've talked about all these different protocols and gateways and things that can make up your cloud native APIs, we're going to talk a little bit about architecture. There are typically two kinds. So first up is Greenfield. I was super excited to hear Ajay's talk. There was actually no communication between Ajay and myself and Olga, but he pretty much laid out the principles for our talk really, really well in his keynote. So what does Greenfield mean? This means that there's no existing applications. It's all new. This is really exciting for builders because it allows us to pick the right tool for the job, right? Next slide. Our restrictions aren't based on an existing technology, but on other factors, and they can vary wildly across organizations. It could be budget, it could be personnel, like who you have on teams or who you plan to hire on teams, how quickly you want to get this thing to market, and what are the requirements, right? Where those requirements come from. But it allows freedom of choice. This is one of those things that is the two-edged sword, right? It can be really, really nice and exciting, but it also can comes with consequences. For every choice, there's a consequence. So this allows you to choose your container service, whether that's Kubernetes or our new platform like Tanzu Application Platform. You get to choose programming languages. Which is really nice. These gateways and protocols like RSocket that we've talked about are all language independent, right? Which is really, really nice. And you can pick the protocols that you need, whether that's RSocket, whether you need HTTP, some other binary protocol, or messaging like RabbitMQ and Kafka.
But we all know that life is not that pretty always. We don't always just get greenfield projects where we can do whatever we want. Very often we work with legacy or often also so-called heritage systems, which tend to be old, big, having quite a lot of technical depth. However, they're also very important because they are often vital for our business. So they're a core point of our systems and of our business functionalities, and they really allow us to serve our customers. So they're also very good in this way, and we cannot just throw them and start building something new very often. But what we need to do, or what we would like to do, because we want to have this functionality running all the time, but we don't necessarily want to keep acquiring technical debt, is being able to start changing them slowly and adapt them. So very often what is done is more modernizing such architecture by areas or components. Let's say we have a monolith. We will often start by thinking about what our banded contexts are in this monolith, and then dividing it into modules until it becomes a modulith. And then maybe some of these modules we want to be able to scale them fast. So we will actually turn them into separate microservices. And if we imagine that we have this kind of legacy service, and then a newer part of our ecosystem which uses RSocket to communicate and has the RSocket broker at its part, and then we would like to make it work together, that is a kind of situation exactly where we will use the HTTP RSocket bridge or any other adapter. You could well also have built that adapter on your own. We just thought it would be useful if we provided one for you. So this is a kind of approach or a kind of architecture change that we will be trying to showcase in the demo. And in that demo, we will see a loan service where people are applying to get a loan, and then that service needs to communicate with a new RSocket-based verification service to check if that customer is fine. Basically, in our super simple use case, if that customer is old enough. And then we will have our RSocket broker and, of course, RSocket verification service instances running, and we will have our gateway. So a Spring Cloud gateway. However, as we will show, it will also be an HTTP RSocket bridge at the same time. And we will be sending requests from the loan service through that gateway / RSocket HTTP bridge to the RSocket broker, then passing it on to get a response from the RSocket-based verification service, and all the way back. So let's take a look at the code. And let's start with the broker.
So to start off, it's awesome that we have plenty of time to talk through the code and things. We will have links to this repository so you can look over it yourself at the end. So we have plenty of time here. So first, the broker is being built as part of the reactive foundation. So the group ID is io.rsocket. It is built using Spring Boot, and it's RSocket integration specifically. Likely in the future, we plan on having the broker distributed as a container, so you don't have to build a Java project for each node that you need. But for now, it's easy, very, very simple to create a Java project for a broker. So now let's go ahead and look at its configuration. So in this particular case, this is showing you typically have multiple nodes. So we're using profiles here for the different nodes and the different ports that they run on. We're using hard-coded IDs. Each node in the broker cluster, including all of the services that connect to the broker, have to have a unique ID. So we're using hard-coded ones here just so that it's easy to view in the logs, but typically you would leave this out in the broker. A node would be auto-generated. We have some logging and we set our ports. And in that second one, we're only going to we're only going to run one node, but if you were to run multiple, you would need to connect to a seed node. And also in the future, we'll be able to use some kind of service discovery or the platform that you're running on to discover those other broker nodes. So that's it. The broker application is super, super simple. Basically, it's just a Spring Boot application and then that configuration. And there's nothing else you really need to do to get the broker application running. So let's look at our verification service. So again, built on top of Spring Boot, and it's RSocket integration. And then the other dependency here is the routing client. This client is built in Java. There's a straight up Java version. So if you're not using Spring, you can integrate. But since we are using Spring Boot, this will allow us to do a lot via configuration. So let's first look at our configuration for this service. Again, hard-coded ID. Typically, you wouldn't need that. So some interesting things here under the IO RSocket routing client namespace. First is a service name. You heard Olga mention those well-known keys. Well, service name is one of those. And it is really the only required tag that we need. So in this case, we have verification service. We also have an instance name. This is nice to be able to distinguish one instance over another. Other tags that could be put here are things like a region or a version or other things. And those are nice because you could be able to query services that are in a particular region or only query a particular version of a service. Then, of course, we have to connect to the broker. And so that's what those ports were at the top, host and port there. We're connecting over TCP, which is the default port right now, the default protocol that we're using, but it could be WebSockets and others in the future. And again, if we're running another instance, scroll down a little bit, we have a new route ID, and then we change the instance name to something unique. Now, instance name could come from an environment variable. I know lots of things, lots of platforms have some kind of ID that is unique to the instance or the container that is running. So that gets us all connected to the broker. Now, in this case, we actually have code to show you. Most of it is fairly basic. Our customer has an email, or it has some names and a date of birth, excuse me. So
yeah, an ID.
And an ID, pretty simple. We have a service. Basically, the service says if the user, based on their age, is eligible to receive a loan. So if they're under 18, did I get it right?
They're over, at least 18.
Yes, if they're 18 or older, they're eligible. If they're under, they are not. So in this case, this class is a @controller. If you scroll up to the top real quick, so Spring @controller, and then we used @message mapping, which comes from Spring Framework, which is the and when it's coupled with RSocket, this is how you can write a simple RSocket message-based service. So this is a request response because there's a single parameter coming in and a mono of a single parameter going out. That means one in Project Reactor terms. So pretty simple service that we have going on here that is connected directly to the broker. Again, notice there's no way for anyone to make an incoming connection to this service. It only connects to the broker.
Yeah, and then we have our loan service, which is for our demo, the legacy bit that speaks in HTTP. So it is actually using web flags, Spring web flags, and then it is also using the Spring Cloud Starter. So this will actually want to connect to a gateway instance and just send HTTP posts. And it doesn't really care that the other services are actually RSocket based. So if we take a look at this service, we have our controller that we'll be doing our requests towards. And then we are using a client, and this is the client that will actually find an appropriate gateway instance. So we're just using service discovery, the discovery client abstraction from Spring Cloud to get instances of gateway. And then we're going to just do a call. Of course, we could also use load balancer there. Also, if you see, we are actually using properties to get some information on the instance ID that we might want to be connecting to. And if that instance ID is present, then we will be actually adding a header to our communication, and we use the RSocket tags header name. This can be customized also in properties, and then we'll be using one of these well-known keys, in this case instance name, to pass it on. So then we only want to get response from a particular instance. Obviously that's not your first scenario, but we just want to show you the possibilities of the bridge. And then if we take a look at the configuration, we have, of course, our gateway data. So normally we would be connecting to service discovery, but since it's a demo, we're using the simple discovery client. So in case you don't know this, you want to use something for tests, for example, you can just add the information of the host and port of your instance in the properties, and Spring Cloud will work with it out of the box. And then we also have our profiles. So if we choose this profile, then we will actually pass this instance ID, which is verification service 2. And then we have our gateway. And that is the interesting bit, because it could be just our usual Spring Cloud gateway instance that, as Spencer has said, it's very easy to run. It's just basically a Spring Boot app. And what you need to do is just to add this dependency, and it will allow you to do a lot of interesting routing and filtering of your requests. And we have also added another one just here, which is converting it also in the RSocket routing HTTP bridge. The HTTP bridge itself uses the routing client underneath, and it will be connecting to the broker. So in order to make anything work in gateway, what we usually want to do is either via code or via properties define some routes. Of course, in a usual application would have many more probably, but we have just created a route for the bridge. And this is super easy. So later on, if you're going to be adding the RSocket bridge to your gateway, you only need to define something like this. So when we get a call at a certain path that we specify, we decide where we want to forward it. And in this case, the verification service is going to be the ID of that service that Spencer has shown you. And then verify is that message mapping endpoint for our RSocket communication. And then, since this is also, as we've said, an RSocket routing client instance, we will have to add some data for the application to know where the broker or where the various broker instances can be found. And another thing to keep in mind is also that in this case, we are showing it with gateway because we assume this is going to be the most useful scenario. And you would have often your gateway running anyway. So you would pass all your HTTP communication, both the requests that just go from one HTTP client to an HTTP server, but also the ones that go from HTTP client to the RSocket server. And you will have this all routed in one place. But if you were not using gateway, you could also just use that bridge dependency, and again, just create your usual simple Spring Boot app, just like this, and have this running. So what we'll be doing, we'll be sending some requests, and we have created 2 JSONs. So we have the fraud JSON with a customer that is simply too young to get a loan in our system anyway. And then we have the valid JSON with a different demo customer that is old enough. And we are going to be sending them. So let's take a look at the ports. As we see, our HTTP service is running at 9180. And we had that verify endpoint. So this is where we are going to send it. And yes, we do get a reply. And just to show you that this is really the case, this is from this verification service here. So let me show you the code. This is where our logic is. So we get the reply, and similarly, if we send a fraud, we will get a response. And this is the way you would communicate. But if you're interested in how things are working under the hood, obviously you could try to just call the gateway directly, which we will do. And we have this instance running at 9081. And this is going to be my request. And as you see this time, I'm actually manually adding this header with the tag with the instance name, so verification service 2. And we are going to run this call. It worked. And just to show you, this is actually the verification service 2. So I have all the other services running here under IntelliJ. And I have run just one other instance of this verification service to be able to pass this profile. So this is the one which has an instance ID that has verification service 2 in it. So I'm going to just close it. And if we try this request again, it will not go. So actually, it will just time out because broker will not find the right instance. And the current logic is such that if you do not find the right instance, then you just don't carry on with the request. And it depends on our timeout settings now entirely when it will time out. But yeah, as you can see, it works seamlessly, and it also integrates with Gateway seamlessly. And we are going to share this with you. It's already there in GitHub. So this is first of the links that we have available here. The only thing that you might want to keep in mind is that you might need to build the services yourself because we are working with snapshots here. But obviously, once they're out of snapshots, then you will not need to do that. And there is also a bunch of links to the related projects and the projects that we have talked about in this presentation.
Yeah, hopefully relatively soon we'll have a release of broker, so you don't have to, and actually the snapshots being published correctly. Yeah, the broker and the client. But it's really amazing how all this works because based on Oleg Zarkowski's work on Spring Cloud Function and RSocket, then Olga's work on creating this bridge and integrating with the gateway was literally zero code. It was really, really amazing to see it work. So props to them for getting that to work, and for Oleg for suggesting it. We were planning on going a different direction, but the Spring team is awesome.
Yeah, we also definitely advise you take a look at Spring Cloud Function and its RSocket integration, because building anything on top of that, as we and I have personally seen while working on this, is really easy and seamless. So really great work by Oleg. Yeah, so thank you very much for being with us during this presentation. And I think now we will be joining this separate Q&A session.
Yep. So those are our Twitter handles. If you want to contact us off, we will be active on Slack directly after this, and also there's a Zoom Q&A link, I think, that will be on the session page as soon as we're done. So thank you all very, very much.
Thank you.
All right, great. Thank you, Olga and Spencer. That was some great stuff. I really enjoyed hearing about all the RSocket goodness in that session. Let's keep the conversation going, and there's going to be a Q&A session and in Slack, as well as there's going to be a link to the Zoom for the Zoom room for the Q&A. So check that out. We're going to take a small break, and we'll be back with Ryan Baxter.